Hello everyone, welcome back to my channel where we're going to be going through the hands-on machine learning book chapter by chapter. Today we're going to be creating a model and dashboard that does an Airbnb price predictor specifically for Chicago, but as we get into the video, if you'd like to change out the city and do something that's closer to home or something like that, you're totally able to get this data yourself on. I got this from inside Airbnb.net or .com, I think. I'll be sure to list that in the description. This chapter is really long, and it sprinkles some machine learning algorithms in the text. But I think it's really meant to give you an idea of how to build a machine learning project end to end, just on a micro scale. It goes through cleaning the data, feature engineering the data, playing around, exploring with the data. And so we're going to be doing a little bit of that, but with our own data set, just to give some novelty, because I think a lot of the exercises and examples they give you in the book, I think if you'd like to go through that, totally fine, but wanted to do something that might be a little bit different. Some of the algorithms that they dive into this chapter are linear regression and random forest. I won't be spending too much time on random forests just because there's a chapter that comes up later in the book. I think it's chapter 7 where they actually go through random forests, and so I think that'll be a really cool project and algorithm that I'll save so we can actually do a deep dive in that. But we will be using the random forest model itself, but I'll be focusing mainly on explaining and talking about linear regression because I think it's a great algorithm to break way into when you're learning machine learning systems. So yeah. So linear regression is a supervised learning algorithm, which means when we're providing the data to the model, we're providing it with data and training examples that already have the value that we're trying to predict, right? So in the case of, right, the data that I have for my Chicago listing, right, this is an example of a data set, and you can see that this has some columns, some rows that has all of the information related to each individual listing. And so you can think of each of these columns as a feature, right? And each row would be a training example, right? So for this example, we have the features for this specific listing or row would be the name Hyde Park Walk, University of Chicago, host name is Rebecca, the neighborhood is Hyde Park, the longitude, latitude, right? And so in this example, we have what we're trying to predict is the price. And so that's what I mean by supervised learning algorithm, that in the data sample, we have the value that we're trying to predict to help it learn if there are any patterns between all of the rest of the features here, right? And the final value, which is that price. And so when we're talking about data, we often talk about its features, like I said here, right? The name, host ID, reviews per month, calculated host listings, its availability. And in the book, they provide housing data in California, and what they want you to do is predict the median housing value of a house given certain features. And this is what one feature vector might look like. What one row might look like in that data set, where you have a housing district, right, and then you have all of its certain features, which would be the columns in that, right? Just to kind of think about this in maybe the most familiar way, the way that you're most familiar with, right? If you have like an Excel sheet, right, or CSV file, right, each of those columns has a set of values that corresponds to a specific feature, right? So you'd have longitude, latitude, total rooms, etc. And the model's job is going to try to predict the value given those certain features. And so essentially the example in the book is assuming there's a linear relationship between all of these features that we have and the median housing value. So we're assuming that there's a linear relationship between the location, the number of bedrooms, its proximity to the ocean, the median house value for that district. And because we're assuming that a linear relationship exists between these features, we can use the linear regression algorithm to model it. And to put it simply, linear regression is simply a linear algorithm, right, that finds an ideal set of parameters. Sometimes these parameters are called weights or theta values of vector theta, right, for each feature provided in the training set to predict what you want it to predict a y value. If you're familiar with kind of pre-algebra or algebra, if you're familiar with y is equal to mx plus b, right, you can think of theta as playing a similar role to slope m. The difference is that in linear regression, we usually have many features. So we have a separate theta value, a separate weight parameter for each feature. So instead of y is equal to mx plus b, you'll have something like this, where each theta is the weight for its corresponding feature, right? So I think in the example, the first feature was longitude or latitude, number of bedrooms, proximity to ocean, right? This would be x1, x2, all the way up to x10. And then you have your theta 0, which is your bias term, right? You can think of it to your y-intercept if you were thinking of like a simple linear equation. And this y on the left side is referred to as y hat, which is universally referred to as your predicted y value. And so if you have any experience with basic algebra, the concept of thetas is pretty intuitive. It's basically answering the question, how much does this feature affect the final outcome, right? In the assumption that the relationship between my features and the value that I want to predict is linear, how much does this feature affect the final outcome? So with houses, right, typically the number of bedrooms that you have means the house is going to be more expensive, right? And because of that, the theta value associated with bedrooms is going to be positive. Basically saying as the number of bedrooms increases, for a house or even a housing district, we can expect that final output value to increase as well. And let's say in some world, as you increase in latitude, right, the housing value decreases. Because of that relationship, right, as one increases, the other decreases, we can expect the theta value for, let's say, latitude to be negative, right? And so this is what's happening under the hood. Your linear regression is creating an equation, right, to help it predict values for the relationship between the features in your data set and its final outcome. And so the way that it does this, during training, right, the model's constantly asking itself, are my predictions getting better or worse? It answers that by calculating something called loss. And I wanna make sure I really explain this well, because loss is super important in understanding supervised learning algorithms, because it comes up in almost every single one that I can think of. And so let's say as it's training, right, because again, the job of the model is to find ideal parameters. So it's gonna keep going through iterations to find ideal weights, theta, parameters to find an equation that is going to predict the best value for a housing, for a data example on average. So let's say the first time that the model makes its predictions, right? The first time it goes through its iteration process of finding ideal parameters, imagine that it predicts 0 for every single house, right? So let's say in our data set, in our very simple data set, we have a bunch of housing, the median house value, and then this red line at the bottom can be considered, what your model predicted, right? So when it's finding the average error, the average loss, how far it is from the actual y value, you're going to see that the distance between the black dots and this red line at the bottom is going to be really high, right? If we're looking for a linear slope, we probably expect more of a diagonal line, right? But your model right now is finding a bunch of zeros, and so basically your loss is going to be really high. And so what it's going to be doing is trying to find values where it can get closer and closer to those black dots on a line through a linear equation. And the way that it does this, the way that it measures this loss, right, is going to be something called mean squared error, which they bring up in the book. And the best way to visualize mean squared error, right, is to imagine drawing a square where each side is equal to the error for each data point, right? And so it looks something like this. And because the area of a square is, its side squared side by side, the area represents the squared error, right? So the mean squared error, basically you find the squared error between each point and you take the average of it, right? By dividing it by the number of rows that you have. And we do this for a couple of reasons. So the first one being, you always want to have an error that's positive, so you square it to make it positive, to never have a negative error, right? And then also, what's happening is when you square these values, the error for values that are really far from the predicted line, it gets punished more. So an error of 4, right, counts twice as much as an error of 2. So if it's 2 values, right, from the actual value, if your model predicts only 2 units away from the actual value, right, that's going to count 4 times less as if it were 4 units away, right? Even though it's only twice as much, but 2 squared versus 4 squared is 4 times as much. And so that's basically what's happening. And so this is kind of what I would say the process actually looks like here in this video, right? So it's trying to find an error that gets you as close as possible as it possibly can to all of these data points in the data set. That's kind of what's happening under the hood. And it uses and it goes through a process of gradient descent, which I could probably spend so much time on, but I'm going to try to keep this light. But I think the best way to describe gradient descent is to imagine that you're standing on a hilly landscape and your goal is to find the lowest point possible, right? Imagine you're on some mountain, maybe with your eyes closed, and you look around and you take a step downhill and you keep repeating this process until you can't go any lower. And that's basically what's happening in this process, right? Is it's going to keep trying to get as close as it possibly can on average to the lowest amount of error that it can possibly go to. So to put this all together, when your model receives data, right, when your linear regression model receives data, it's going to create a linear equation that's going to keep adjusting its theta values, or its weight, right, the coefficient for each of those features, measuring its loss through mean squared error, where every time it adjusts the theta values, it's calculating its error to say, hey, did my error get better or worse as I shifted this value? Imagine you're dealing with one feature, basically y is equal to mx plus b, right? Like, the process of doing that can be really straightforward. However, when you're dealing with, for example, like the example that they have in a book, where you have 10 different features, this process of finding the ideal coefficients or parameters of vector theta that gives you as close as you possibly can to your predicted value, as close as it possibly can to the actual y value, it gets really complicated. So I hope that was helpful. I realized that was very high level, but I wanted to give context to the algorithm itself, because really what I find what's happening in the book is it kind of sprinkles concepts in and out, and hopefully I did not confuse you more, but rather made this easier to understand when they're talking about mean squared error and things of that sort in the book. This is kind of what's happening under the hood. So with that being said, let's get into the project. I think I also really went through some of these concepts to give more context to what I'll be talking about in actually going through the project. So in the description, there should be link the starter project to go through this, to create the price predictor dashboard that we're going to be creating. So if you want to git clone that, and then also in the previous video I talked about going through and creating a conda environment. So it's super simple. I think you just have to do like conda activate, set your Python is equal to select the version that you want, and then just do pip install -r requirements.txt. And if you're using Visual Studio Code, you can go up here. I think this is the one that I just created, but this is the one I'm using, basically the same thing. Nice. So let's get started. So one of the things they talk about in the video is, I'm sorry, not the video, the book is framing the question, right, to give you some context and I guess some purpose in what you're going to be doing and building. So let's imagine you're a data scientist contracted by a property management company in Chicago that manages, 50 plus Airbnb listings. They're losing money because hosts are manually setting prices, some overpricing, some underpricing. And so basically either money's being left on the table if you're underpricing, or if they're being overpriced, they're just basically sitting empty, right? And so they come to you and ask, hey, can we build a tool where a host's input their listing details and we give them a recommended nightly price, right? And so first we're going to analyze and play around with the data a bit to understand it better. Then we're going to build a model that predicts a price giving, the listing features. And then we're going to build a dashboard using Streamlit that actually gives us kind of a dashboard view of everything that we did, broken down by our process. And so yeah, let's get into it. Again, I got this data from inside Airbnb.com. So if you want to choose your own city or a different, place, feel free to do that. We're going to be first working on inside of a Jupyter notebook. And then we'll we'll export this and basically make its own file and function called pipeline. But for the moment, let's load the data. So I'm gonna try to explain some of the imports here as I'm going through it, but for the sake of time going through, let's create a function that loads the data and it's going to read the raw CSV data that we have here into a data frame. This is simply loading it. We're not going to be modifying anything here. So def load data, file path, string, and it's going to be returning a data frame, which is going to give us the ability to really play around with this data in the way that we need to and want to. So df is going to be equal to p.read CSV. PD stands for pandas, and we have the file path. We're going to have a function that's going to take a file path, right? And then we're going to say we want to print, we're going to say f, load it. We're going to say length, df, taking the length of the data frame, shape. It's going to give us the number of columns we have in our data set. Oops, I think I did something. There we go. Columns, right? And then we're going to return the data frame that we have. So just to make sure this works, file path is equal to OS operating system. This gives you the OS module gives you access to your operating system, so we can do things like this. Join os.getCWV. And we're going to say data/Chicago listings. Maybe can we copy this? Whoops. So we'll just do this. .csv, and then we'll say df. So the raw data frame is going to be equal to load data, file path, and then we're going to say, so df info and df raw dot info, and then df raw dot describe. This is basically going to give us some high-level information about our data set. So let's import these. I'm going to save this for when we have some shared variables at the bottom. But so here, so just looking at all of this stuff, right? So we see now we have about 8,700 rows. It looks like, for example, neighborhood group doesn't have anything, and I think that is because, so I took a look at some of the other data. So neighborhood group would be like a borough. So New York City would have this data, but in Chicago we don't have boroughs. So neighborhood group is just it's empty, I think, in the data set. Some of the listings are missing host name, right? Like this is this is the time you would use to kind of like give you an idea of what you need to do to clean your data, right? And so what describe does is it for values for columns that have numeric types, right? So latitude, longitude, minimum nights, it's going to just run a very high level statistical analysis. So what's the mean, the standard deviation? And so we'll see, right, like for some of these, for longitude and latitude, this makes sense what this looks like, because basically what this is giving you is like the outer limits of the city of Chicago, right? Probably. And then the price, I think this will be really interesting, and we'll dive into this a bit later, right? Like we see the max for the price. There's some listings in here that have a $50,000 nightly rate, which is crazy, and we'll have to fix that in the future. We have minimum nights, which makes sense. It looks like the max, some people let them stay for, you have to stay for at least a year, it sounds like. And yeah, number of reviews. So this kind of gives you a high level, like what's happening in your data set, and it'll definitely help inform what you have to do for cleaning our data, which brings me to my next section. And so before we do that, another really cool thing you can do is just head, and this will give you exactly what those like first 5 rows, I think, yeah, what the first 5 rows look like, just to give you more context. I did show a little bit of that in the beginning in the Excel sheet, but yeah, another really useful function that you can use. So to clean the data, whoops, no, didn't mean to do that. So to clean data, we're gonna get our function def clean data, and it's gonna take a data frame, pd.dataframe, and it's gonna take pd.dataframe. I'm sorry, it's gonna return another data frame. And so this is really when we start feed information to our model that we think will and will not be useful, right? And so this brings me to the first thing that we're going to be doing, and we're going to be dropping some columns. The columns that we're going to be dropping for now are going to be ID. We're going to drop the name, the host ID, the host name, the license, and the neighborhood group. One being that, so when you're feeding features to your linear regression algorithm or model, right, it has to be, the values have to be numeric. So that's why we're going to be dropping name and host name. I think also dropping host name gets rid of potential bias, right? Like, we don't want it to think that, you know, John versus Juan, right? Like, we don't want it to think that there's a difference in the quality of, you know, your Airbnb because of the name of the host, right? License isn't going to be useful for us. Host ID isn't going to be useful for us. ID isn't going to be useful for us. This is just a unique identifier that probably Airbnb has, I'm guessing, or that the data set that was given to us has. Neighborhood group, it's empty. It's not useful for us. And so yeah, we're gonna clean these up and drop some of this. So we're gonna have columns is equal to an array, and we're gonna say ID. We're gonna say name. We're gonna have host ID, host name, license, and neighborhood. Oh, that's a thing. So I think this data set is comes from somewhere in Europe because they spell neighborhood with an OU. Okay, so we're gonna drop these columns, and then another thing we're gonna drop is we're gonna drop the rows without a price value. And the reason we're gonna do that is because, like I said, supervised learning algorithm means that you have to have examples that have the value that you're trying to predict. And so really, if a row does not have this price value, it's pretty much we can't do anything with it, right? And so if you see here, there's about 800 rows that don't have a price value. So we have to get rid of them because they're not going to be useful in training our value and training our model, sorry. So dot reset index, and that basically says that after you drop it, don't use the re-index it, basically. So if you have a row if you drop row 2, basically row 3 becomes row 2, and then it follows the subsequent order after that. Another thing we're gonna do to clean the data is, so instead of last review, I think what is going to be, and this kind of goes into feature engineering, but we can call it cleaning for now, but basically we're going to encode last review to has been reviewed, because if you look into last review, there's about, I don't know, almost 2,000, like 1,700 rows that don't have a review, which if it doesn't have a value, we can assume that means that it's probably never been reviewed. And so instead of dropping these rows and making our making our data set even smaller than what it already is, because this is probably considered a really small data set, we're going to actually calculate it to be, we're going to create another column really and say, or another feature, I should say, has been reviewed, and we're going to say is equal to df last review. And we're going to say anything that doesn't have a value, we're going to encode it as type int, and this will be, it'll basically get converted to a 0 or 1. And another thing we're going to do, similar to what we just talked about, days since last reviews, if it's never been reviewed, then we're going to calculate that. Because last review, I think it's here, right? Same thing, reviews per month. If it doesn't have a review, then there's no value there. So we're gonna go ahead and say df days since last review is equal to pd.toDateTime. We're gonna say today, and then we're gonna say minus pd.toDateTime df last review, and then we're gonna say errors is equal to coerce. And what that means is, so when you do coerce, what it means is that if there is no, if for example there's no last review, what I think that means is that it's going to be converted to a non-date type. It's going to be converted to whatever the date type, whatever the not date, whatever the null value is for the date time type. And then we're going to have this be as type int. Cool. Let's see. I just want to make sure this looks right. Cool. This looks good to me. I gotta add. It looks good now. Cool. Okay. And then we're gonna say df reviews per month. Another thing that we're gonna fill in, because if you don't have any reviews, I think the value, the row value is just blank. Reviews per month dot fill in non-null values to 0. And then going back to the price issue, right? So we saw that there are some values here where the nightly price is $50,000 a month, which is just crazy. That has to be just not right. I mean, coming from Chicago, I know I'm like very unlikely that there are some values that you have to pay $50,000 a night to stay in. So what I want to do is get rid of those outliers, which is super common in machine learning because a lot of times those outliers might just be like completely wrong. And so I want to see what is the 1 percentile. And we're going to say print I'm upper, right? And we're going to say upper. And then let's see. So we have df.clean. Df underscore clean is equal to clean data df raw. Let's see if this works, if we get some errors. did we run this? Yeah, we did. Okay. We got error here. Yeah, I knew there was gonna be something wrong here. So what's going on here? Today minus PD today time. DF last review errors. dt.days fill in a dot s type int. Oh, so yeah, this should not be. It should just be s type. Cool. All right, let's see. This should work now. Amazing. So the upper value right now is about 3,000, which also seems crazy. Let's see. Let's play around with this for a bit. 0, 1. Okay. Let's see. Okay. I think this works. Just set that as our upper bound. And then basically what we're going to do is we're going to filter out in our data frame. We're going to say price anything. We're going to just keep anything that's less than or equal to the upper bound. And one other thing that we're going to add into this is something that's actually really common in when you're transforming your data. And I recognize that it might not be the most intuitive, but we're actually going to transform our prices to the log of our prices. And this is something that I've come to the conclusion with after playing around with it, and this probably might not be the most intuitive, right, being 10-15 minutes into the data set, but the reason we're going to do this is because when we think about pricing, it's actually, the reality is that when we're thinking about pricing, we're often doing it in relative terms. So let's say you're estimating a pair of sneakers and a motorcycle, right, an electric motorcycle, let's say. And let's say the cost for the shoes is $100 and the cost for the motorcycle is $2,000. Let's say when you're predicting the price of the pair of shoes, you say $50. And for the price of your motorcycle, you predict $19.50. So you're off by both by $50. However, your error for the shoes is 50%, while the error for the motorcycle is 2.5%. However, when like thinking about to how error is calculated, right? When we went back to mean squared error, you know, your error 50 squared, right? The error is going to be the same. When in reality, you're actually a lot closer to the motorcycle, right? Because the error for the motorcycle was only 2.5%. And so without log transforming your price column, the model is going to treat both error, I guess, any error that is off by the same amount equally, where in reality, a listing for $3,000 a night versus $100, being off by $50 for a $3,000 listing, you're a lot closer than you are if you're off by $50 for a $100 listing. So, for example, 10 squared is equal to 100. The log of 100 is 2. Right, and so let's say for these prices we have 100, 200, 400, 800, 1600, 3200. The log of that is going to be 2, 2.3, etc. to 3.5. And so what it really does is it also helps our model predict prices because it compresses those really large numbers and stretches the really small ones. And it helps with, because we have such a wide range in our data set, right? Like we saw the upper bound for this is 3,300, but if you're going back to this, the average price is 600. So you have a really wide range of data, and even here, right, you have 75% of your data is going to be $240 or less. But again, we have 0.1%, our 1 percentile, right, is that $3,300 $3,300 a night. And so here we can just say the price log is equal to p.log 1p, there we go, df price. And so now we're gonna say print is equal to f after cleaning data frame. It's going to give us how many rows we have. Frame. Let's see what we got. Nice. So we have about 7,800 rows now. Cool. Now this is probably maybe the most fun part is like being able to actually visualize and see your data. So let's go into exploring our data. So we're going to create a function, def is equal to explore data. Yeah, if it's going to take up data frame, p.data frame. And then it's going to say none. It's going to return none, sorry. And so the first thing we're going to do to visualize what we have is a price distribution graph. So we're going to say your price. And we're going to do this for both the price and the price log, just to, again, I talked about some of this stuff like 2 minutes ago about the distribution of our data. But it's always nice to see it. So fixed size, 10.4. Fixed size is equal to, right, plt.xlabel price. PLT, by the way, is matplot plot diagram basically. So just so you all know, PLT label. This is my first time, I think, explaining what I'm doing while also typing, so I'm making a lot of typing mistakes. I guess it's just a muscle I gotta keep flexing. So, and then we'll just do plt.type layout, which I think is just for formatting stuff, to make it show more nicely. And then we're gonna do the same thing for price log. So instead of this, price, excuse me, price log. We're gonna say log of price. And then let's see what that gives us so far. So I'm gonna say explore data. Should be, what do we call it? df clean. Let's see, what do we got here? Oh, I know what's happening. I did not return df. So there's nothing here this should work now. There we go. I'm gonna get rid of this to make my screen bigger. So yeah, this is the distribution of price, and you can see how this is skewed to the right a lot, and it's almost even hard to see some of those the counts down here, right? But it looks like this is probably somewhere like 200 it seems like most of them are. Whereas, I think that's, what does the median say for this? Oh, it's not here. But I'm assuming it's probably somewhere around 200. But then you can see once we do the log price of the prices, it gives us a much more normal distribution of the prices. Then, so next we're going to, do something similar, but for all of the different neighborhoods. So figure, set the size, fixed size is equal to 1020. ADF neighborhood or hood dot value counts dot plot. Oh boy. Dot plot. Kind is equal to bar h. PLT dot title is equal to listings per neighborhood. Right. I'm gonna get rid of this U. PLT dot type layout, which I have to be honest, I don't remember exactly what it does, but I know it helps with making sure everything appears on the screen. Let's see, everything looking good. So we have all of our different neighborhoods in Chicago, which we'll see later when we do a map of the values, right? But looks like most of, if you're familiar with Chicago geography, right, most of these listings are near or around the loop, right? So near North Side, I think, is like maybe literally what the exact like just the exact neighborhood is of like the center business district, right? What downtown Chicago is, or just right outside of it. And so one thing I also want to do is create a scatter map to see where all of our listings are. And so we're gonna draw a relationship between basically the size. I'm sorry, how many there are, or how many reviews there are, and we'll kind of see some of the density of where they are, and the relationship with its price. So x is equal to longitude. S is equal to DF is number of reviews. Which is going to give us the dot size, right? It's going to tell us how big to draw those dots that we'll see on the graph. We're going to divide it by 10 to give it some scale. C is equal to price log, which is going to give us the dot color, like I mentioned before. C map is going to be equal to jet, which is our color map. Color bar true, which is going to give us the color legend on the side. Share x is equal to false. Fig size is equal to 10.7. And then we're going to say the title is equal to listings by location. Let's format the cell, makes this easier to see. Let's see what we got. Nice. So over here is the Lake Michigan, and then we can see here all of our different listings. I personally really did not like this graph because it was kind of hard to see in a geographical sense. And so for the sake of time, I'm just going to copy this, and feel free to use this as well. But what this will do is kind of give us, and I'm hoping this works, because I've been with Visual Studio Code, sometimes it doesn't render automatically, unfortunately. So let's see if this shows us. This is basically going to be the same thing, but using an actual map that will make it look better. And yeah, it doesn't look like it's going to, oh no, let's see. No, I have to reload this. So let's save it. Let's X out of here, and then let's Visual Studio Code. Let's open this back up. Let's see. Let's see if it works. Nice. So this gives us more of a, gives us a little bit more context of like the geography of Chicago, because with this graph down here, right, this gives us a lot more information, although the graph down here does give us longitude and latitude. But just looking at this, and also if you have any context about Chicago, like this looks about right, you have like downtown Chicago here, which seems like this is where a lot of listings are, right? And this will give us more information when you're exploring the data, when we get into more of the feature engineering part of things, of what we might want to signal to our model, what's important, right? So proximity to the lake, right? Even as we go further south and further away from the downtown area, right? It looks like as we get closer to the lake, there seems to be more density here, whereas like down here, right? Like looking from here to this, right? The density increases a lot as you get closer to the lake, and so that might signal that maybe there is more desire to be near the lake, which might not be super obvious when just looking at, you know, when the model is looking at the data with the raw values that it has. And so lastly, we're going to create a correlation map, which is also going to be another way that we give us some insight into what values might be correlated to one another, what relationships might exist between the values that we have and our data set, or the features that we have on our data set. So mask, we have this numeric only means to only create correlations based on the values in the data set that has numeric values. Whoops. Dot one, like, yep. Core D type, data type is going to be Boolean. Then we have is equal to plot.subplots. Fig size is going to be equal to fig size is equal to 11.9. CMap, color map is going to be equal to start diverging palette 230 20 scmap true. And then we're going to do sns.heatmap. We're going to say core mask is equal to mask, CMap is equal to CMap, Vmax is equal to 0.3, which caps our color scale, as you'll see, lower to 0.3. Center is going to be 0. Square is going to be equal to true. Lane width 5. C bar KWS is going to be equal to an object. shrink 0.5. And then we're going to say PLD to title is equal to feature correlation matrix before feature engineering and we're going to show. And let's see if we get any errors. Whoops. I'm going to comment this out because it looks like I'm going to comment the map out because it looks like it's just not working again. And I have a feeling this is probably a Visual Studio Code thing. Cool. So for our correlation map, so this is what we have here. Longitude, latitude seems to be very cheaply correlated, which makes sense when dealing with the geography of Chicago, right? Like it can only be within certain bounds, so makes sense. Price seems to be correlated, well, obviously with price law, but we see there's some very faint positive correlations with number of reviews, its availability. There seems to be a correlation between if it's been reviewed and the number of listings that it has. And this is one of the things that I was talking about with the challenging part of working with data, as we'll see later in the project. But you can see now that a lot of what we have here, there seems to be some weak correlations in between some of the features, and this is when we'll get into the engineering feature to kind of like feed our our model any other additional correlations that we think might exist. And so we'll be able to see some of that in the next step. So let's go here. So we're gonna have a return. No. By the way, all of this data exploration stuff is going to be dropped in when we actually do the pipeline, because this is not stuff that we want to get into production. This would be just for our own sake, right? Like this is super expedited what we're doing. And this would be something that you might do on your own when you're playing around with the data to see what's happening, what relationships exist, give you a thought process on how to think about the data. And I think this won't be necessary. We'll be doing our own kind of summary of the exploration that we did in Streamlit. Nice. So let's get down to our engineering features. So we're going to create a function, engineer features. It's going to take a data frame. It's going to return a data frame. And so the first thing we want to do, right, is by guess, right, is all of this really high density here. And given, this is probably my bias being introduced, right, but given its proximity to the loop in the center business district, one feature we're going to engineer is going to be the distance to the center, right? So how far is the listing from the central business district, essentially? And so the longitude and latitude for that is going to be 441.8781, and we're going to have negative 87.6298. Looks good. And then we're going to create a feature dist to center. Is going to be equal to, right, if you remember distance, it's going to be the square root of, I believe it's like, I think it was like y2 minus y1 plus x2 minus x1. But in our sense, that's going to be just longitude and latitude. So we're going to say df latitude, minus Chicago Center 0 plus, squared plus df longitude to longitude minus Chicago Center 1 squared. Right, and then we have that, and then another one that we're going to do is create, we're going to try to differentiate between the different types of listing, right, versus what is the minimum number of nights that you have to stay. And the reason we're doing that is because, you know, I think we saw in the data above that one of the minimum number of nights you have to stay, right? So the minimum nights you have to stay, it looks like from our describe function here was 365 days. So that means that there are listings in the data set where you have to at least stay a year. And I think the behavior in which that the pricing for that is probably a lot different than if you have to stay there for at least a week, right? Because you're going to be treating it basically like a rental property for staying there for a year, right? And so you might want to say, I want to give my value, $20 a month because I know, right, that I'll be getting X amount of dollars from that for a year, rather than trying to do a pricing based on, I might have someone stay here once a month for a week, and so, right, so the pricing structure for that might be a lot different. So we're going to say df is df min number of nights, min nights, bin is going to be equal to pd.cut df minimum nights bins is equal to 0, 1, 3, 3, 7, 30, 3, 6, 5. And we're going to create labels for these, and we're going to say nightly, right, short term, you have to stay for at least a week, monthly, and then long term. And so basically what we're going to be doing is, for the values that these rows have for the minimum number of nights, we're going to be putting them in bins. So that way we can kind of categorize what these kind of listings are, and hopefully that will help our model predict these values better. So, and with that, we're going to drop some more columns, which will be, we're going to drop latitude, longitude, and then we're going to drop minimum nights. And then we're going to reset index, which I've set before, just make sure that the rows are in sequential order. And then we're going to return df. So we're going to say df engineered is equal to engineer features df clean.copy. Let's see if this works. We get the errors. Nice. So, looks like something didn't work. mp.square root wait, let me just say df engineered, just to see if this worked. Dot info. Okay, looks good. Oh, distance to center does not look good. Okay, that's empty. Good to know. So let's see. np.square root. Oh, I know. I'm missing I think this has to be this, right? Oops. Need another one. Oh, I put this in the wrong place. So it should be this. Nice. Okay. Awesome. Moving along. So the next couple of sections are going to be kind of related. For this step, we're going to be splitting the data. And so what that means is that we're going to be splitting the data into a training set and a test set. But before I do that, I want to explain what that means. So there's a training set, a test set, but there's also a validation set. And so you can think about it as studying for an exam. So your training set is your study material, right? And I was talking about this, I believe, even in the last video. And I didn't want to get too deep into it because it's like it's a whole other section, but your training set is your study material, right? Your model learns from this. So that's your training set, but your validation set is like practice test that you take while studying. So it's separate from the training set. All of this data comes from the same place. It comes from the same data that you feed it. So you use it to check how you're doing and make decisions while training your model, right? So you'll have a training set that your model actually trains on, but then it uses your validation set to say like how good or bad am I going? How good or bad is how good or bad are my decisions? Your test set can be thought of as like your actual final exam, and so you only look at it once at the very end to get an honest measure of how well your model is actually performing. And so this would be common as you're doing the feature engineering, is you use that test set to see like, hey, is my model doing well? Do I need to do any other feature engineering? Are there major gaps in my data that I'm not looking at? And this is really where you get to assess your model's performance. And the reason that you keep all of this stuff secret is if you let the model like look at the test set, you basically like give them the answers, your model might actually just memorize the answers. And so this is a super common mistake, and it's called data leakage. And so what you really want to do is keep all of this stuff set one, you want to give your set a validation set to assess its own performance, but then the test set for you to assess how well the model is doing. And so industry standard for all of this stuff is I usually like 70, 15, 15. So 70 is your train set, 15% of your data is your validation set, and then you might leave 15% for just the testing set. And so we're going to be doing an 80-20 for the training test set, and then we're going to do 80-20 again with this within the training set and the validation set, which will give us about 64% of training, 16% of validation, and then 20% for the test set. And so let's get into it. So we're going to say split data. It's going to take a data frame, data frame, test size, float is going to be equal to 0.2, like we just said, and then a random state. Random state makes sure that every time you run this, the test and validation set will always be the same. If you do a different random state, I think this is the default value for the packages that we're using, but whoops, it should be an int. But this makes sure that every single time that we do, we run this, for example, that those data sets are going to be the same. So first thing we're going to be doing is doing a little bit more. We're going to basically stratify our price log column, because what we want to do is have a pretty decent distribution of each of the different types. We want to have an even distribution of all of the different prices that we have in our between our data, between our training and test set, because you want to give your model good data to train itself on. And so if randomly it's choosing all of the price values that where their listings are only $100, when it gets to testing and validating, if it doesn't have a good representation of those different types of that different distribution of data, it'll make it harder to really perfect your model. So in splits is equal to 1. We have a test size is equal to test size. That was passed in here. And then we're going to say random state is equal to random state. Although I do think the default value for that is 42. And then we're going to just go through and we're going to say for training index, test index, and split.split. Say df, and then we're going to say df price log cat train set is equal to df dot lock train index dot drop columns. And again, we're dropping this because we do not want it to actually see what the actual value is. So price is equal to price log cat test set is equal to df dot log test index dot drop columns is equal to price log cat. Let's just do some printing. F train length train set rows pipe test length of test set rows. And then we want to return, whoops, did not mean to do that, is here, return train set test set. Nice. And then what we're going to do to call a train set test set is equal to split data df underscore engineered. Did we return that in the previous function? Nice. Okay. Let's see what we got here. Nice. so this looks good. Just to clarify something, so I'm going to format this entire notebook. So this split.split doesn't actually give you the rows, it just gives you the indices, right? And so that's why we're doing all of this stuff here where we're basically saying for each of the indices that were returned from the split.split, we're put this into the test set, put this into the training set, put this into the test set, and then drop this category column, because the reason we did this was to make sure that there was a somewhat even distribution between all of the different prices, right? And so now we're going to go to our pre-processing. We're almost done, and we're going to be moving on to the actual application and applying the model. Cool. So for step 6, where we actually do the pre-processing, and I say we're almost done, but this is probably one of the longest sections. So we're going to do function pre-process. We're going to do pass in the training set. We're going to pass in the test set. And so we're going to be separating the features from the labels. So we're going to be getting rid of all of the, we're going to be further breaking this down, right? So we have the training set, we have the test set. Remember, test set is left at the end, but we also have to break this down to also give us a validation set within this, training set. But then also we still have all of these categorical columns, right? Remember, I mentioned earlier that linear regression models can only work with numeric values, and so we have to still transfer transform all of this stuff. And so this is where it kind of gets a little bit weird, at least for me, because in order to do this, we have to do this something called a one-hot encode, which basically will give us will help transform all of our categorical non-numerical values to numerical values, so that way the model can actually train on it. So with that being said, let's get into it. So we have y-train full is equal to train set. I also forgot to mention, I think the reason I'm also struggling to type is because at work I use a Dell laptop, or a PC I should say, and I use, for my personal laptop, I use a MacBook, and so I think what's happened is I don't actually type well on either one of them, because I'm constantly switching between the two different keyboards. Cool. So this is our Y training value. This is our basically training values, where it's just going to be the target that we wanted to predict, and then we're getting rid of anything that has the price column. So that's the price plus the price log column that we did, because we don't want, again, that data leakage. We don't want our model training on values that already has that value in there. And so to split this into X train and the X validation, Y train, Y validation is equal to train test split, which is another package that we have above, and it's going to be X train. X train full, and it should be Y train full, and then it should be test size is equal to 0.2, right? So we're further breaking that down. that 80% and taking 20% out of there, and then we're going to do the random state again and reset the random state again, so that way anytime you rerun this, the values are going to be the same. And then this is the encoder we're going to be using, which is going to let us transform our categorical, our non-numerical columns to numerical columns. This is confusing. So basically what it's doing is it's gonna convert these categorical columns to a data frame with proper column names. But how do I explain this? It's creating a categorical column for each type of value that we have in the data set. So for example, for all the different neighborhoods, right, we have Avondale, Lincoln Park, Wicker Park, right? And so what is happening is that it's actually adding a column that's neighborhood Lincoln Park, neighborhood Wicker Park, and it's gonna give a 1 to that row if that's what the neighborhood is, and a 0 if it's not. And what it's going to do is it's gonna drop the first column, because if it's not either, for example, if it's not either Wicker Park or Lincoln Park, it must be Avondale. So I hope that makes sense. This is really confusing, not super intuitive, but it's kind of the way you have to go when you have to work with categorical when you have to work with categorical columns. I think I forgot to mention that I printed this. I copied this. So if you want to just copy this, or if you want to write it out, go ahead. And then we're going to create our own encode function, df, which is going to use our encoder. It's going to be called encoded. It's going to be called encoder.transform df categorical columns, right? And then encoded.df is equal to p.dataframe, encoded columns, encoder.get get feature names out, categorical columns, and we're going to say index is equal to df.index, and we're going to return p.concat, and this is going to give us that shape that I was just talking about earlier. So p.concat df.drop columns categorical columns, encoded df axis is equal to 1. And then basically what we're going to do is just say xtrain is equal to encode xtrain, xval is equal to encode xval here, and then we're going to say xtest is equal to encode xtest. Amazing. Oh, I forgot. I don't even think I have xtest. Oh, I completely forgot this. Okay, we're gonna go back up here. ytest is equal to test set price log. And then we're going to say x test is equal to test set, right, dot drop columns is equal to test set dot filter. We're going to apply regex price. I'm going to say dot columns. Let's see any errors here. Amazing. And then we're going to return xtrain, xval, xtest, ytrain, yval, ytest. Whew. And then we'll just say, copy this, we'll say, this should be 6, right? 1, 2, 3, 4, 5, 6, and we'll just say this is equal to pre-process, train set, test set. Let's format the notebook. How are we looking? Amazing. Alrighty. We are super close. So this is basically the hard stuff has been done, and this is basically, now we're gonna just, we're gonna let the model do all of the hard work for us. So we're gonna plug in our models. We're gonna do definition train models. We're gonna say xtrain. We should be getting xtrain, which is gonna be a pd.dataframe. And then we're gonna get a yframe. Sorry, ytrain, pd.series, right? Because it's just our y values, and it should be return a tuple, right? So we're gonna have our linear regression, and we're gonna have random forest regression. Nice. Again, not gonna spend a ton of time on random forest. I don't think it's worth it. I will say random forest is more powerful, and you'll see it'll give us slightly better results. And hopefully you'll be able to explain that why later in the course. So linear regression. Again, this is coming from up here, from one of the packages up here. Linear regression, model.lr is equal to linear regression, and then we're going to do model lr.fit, and we're going to do it on our xtrain. Sorry, xtrain, ytrain, and then we're going to say print linear regression trained, and then we're going to say model rf random forest is equal to random forest regression. Yeah, again, this is basically telling it how random forest works in a way of basically going through a series of paths to basically see, for example, if I'm going to be $400 or $500 or $450, right? It might say like, is my neighborhood Wicker Park versus Bronzeville? And in that case, it's going to build out a bunch of different trees or different paths, which will help it better estimate. And so this is basically telling it how many different branches to create when it's training itself. And so model fit. Sorry guys, xtrain, ytrain, print random forest regressor trained, and then we're going to say return model lr model rf. Let's see, this is usually, That was quick. Oh, because we didn't call it. Duh. Okay. LR model RF is equal to train models, X train, Y train. Input contains nan. Random forward, random state, model RF dot fit. Model train models. Let's see what's going on here. Okay, I know what's happening. So basically, I did some debugging off screen because I didn't want to take up a bunch of time, but I can see here that there seems to be some values for last review that do not have values, and we must have forgotten to drop this because remember, for last review, I think we said has been reviewed, and then we also did I think it was time since last review, days since, right? Exactly. So we forgot to drop this, I believe, in the clean data set, which would have been here. So I think after price log, what we want to do is do df, because we're not even using it. We say df is equal to df.drop. Columns is equal to last review. And then we want to say reset index drop is equal to true. And then I'm going to format the notebook. Format, whatever. And then I'm going to do run all. Which should get us here. Nice. So our models have been trained. And then let's get into the evaluation of how our models did. So this is going to be a lot of print statements. Whew. Okay, def, evaluate model. Model, X train, Y train, X val, Y val, X test, X test, Y test, name, right, string, cool. And what we really want to know is how well did each of our models perform, and so I'm gonna just put a bunch of print statements because that's what we're basically about to be doing. Alrighty, so we're gonna say we're gonna do this. We're gonna do new line, name. I probably should have left this in because this isn't really super useful to, I guess, machine learning, but whatever. We'll just do this. Looks good, and then we'll just say f train r to the squared power. Which is going to be also known as our variance, model.score. And we'll see how it did on all of our different data sets. So this 0.4f, and then we'll have this train, no, val. I'm going to just copy all of this because this is, I can get rid of this actually, and then we're going to just say train, this should be val, and this should say test, going to say x val, y val, x test, y test. And then we're going to do the same. Whoops, actually. We're going to do y predict, which is basically what we want our model to basically predict a value. We want to see how well does it actually predict something. And x test, right? And then we're going to say the root mean squared error, which is what I talked about earlier, which I'm kind of glad because I was worried that this would be a little out of context, but the log of the root mean squared error is going to be np.square root mean squared error, right? A y test. We're going to say y predicted, the prediction log, right? And then we're going to say n dollars. Well, let me just print this. I would like to print this. We'll just say what is this going to be? Test RMSE dollars, and then we're going to just say RMSE log. Perfect. And then we're going to do the same thing, something similar here. We're going to say, gotta charge my laptop. We're going to say mean squared error, but instead we're going to say, we're going to convert it back to dollars basically, which is going to give us exponent y test, and then we're going to say, do the same thing here. We're going to say y prediction log. Alrighty, and then we're going to just basically say, whoop, this should not be dollars, this should be log scale. Well, let's copy it. Right, and then we're going to say evaluate model. Oh, I'm sorry, I'm going to just copy this, which is probably faster for both me and you. This should not be here. This should be out of the... Okay. Let's see. And so here we have basically how our model did. And so, so what this means, this is variance, which is different from the variance that I think I talked about in the last video, where high variance typically means it's overfitting. What variance means in this context is what percentage of the features explain the outcome, the value, or the price basically. And so what it's saying is that in the training set, in the test set, and the value set, that, for example, in the training set, the features explain 52% of the price. So basically our model is telling us that there's a lot of stuff missing, right? Which I agree, and I think that unfortunately this might not be the best case scenario or the most exciting value, right? Because if you look into, right, the root mean square error, it's saying on average the error is at almost $200, right? which we makes sense for this variance, right, of 52% of the variance. If there's a 52% variance, meaning that it cannot account for the other 48% of why the price is the way that it is, right? And fortunately, random forest is a bit lower, and I think that's one of the reasons why they introduced it in this chapter, was so that you can have a more powerful model, right, to predict. But at the end of the day, they don't really do that much difference, and so this is one of those cases where maybe the data was just not, good enough. And I think one of the reasons for that is that looking at this data set, there's just really there's a lot missing from it. One of the things that I think is missing from it is the rating, right? That's like super important for probably why. I think there's a ton of. I think another thing missing are the amenities. You could probably analyze photos to see how well it actually looks, how well furnished it's look. I think bedrooms and bathrooms are missing. We already said guest ratings, but again, there's a ton of data missing from this. And unfortunately, even from the data set that I found, it was not, I don't even think it was included, right? I think in the data set, if you go to inside.airbnb.com, I think they have the reviews, right? And so I think a really cool extrapolation of this that might help, right, is if you analyze the reviews and the data set, is it positive or negative, right? How positive or negative would you put inside of for each of the listings? And maybe you could manually artifact a rating for it, and maybe that might explain some of the other missing variants or some of the other missing data for predicting the price. I think another really interesting thing is in this random forest, you see the variance is really high, right? It basically is telling you it can account for 95% of why the price is the way that it is. But when you go into the validation test set and the test and the actual test set, it's 63% and 57%, which is a really big difference. And this is really common with random forest, is that it just overfits the training data, and it doesn't actually perform really well on the rest that we have. I think another reason for this could be that we have a really small data set. We only have 5,000 rows, which is super tiny, and talking in machine learning and data science. And so, yeah, I hope this was useful. And I think as I get better and as we go through the course, we'll be able to have some maybe more comprehensive data that will actually give us, and maybe some better engineering feature that will give us, better results in our error. But I think this is really common. And one of the things that, if you ever do decide to present this project of why it failed, because people will ask, right? You will, as much as you need to be equipped in being able to do data engineering and feature engineering and being able to understand what's happening in a machine learning model, people will also really expect you to understand why a model fails and how to adapt and what you would do when a model fails. And so I think, although this might not be the best but the best outcome that, for your first machine learning model, I do think it's super important to also understand what to do and what to do, and understanding why a machine learning model failed or didn't do as well as you'd expect it to. Alrighty, so I think we'll be done, let's see, in about 20 minutes. Last thing we have to do is fill in the predict cell, which will basically have the model predict a value. And I'm gonna just do def predict price is equal to model rf listing input columns, right? The list, so it's going to output predict, right? And then, oops, we'll have this. So we'll have the listing is equal to listing input dot copy. Chicago Center is equal to. I'm gonna copy this. And then what I'm gonna do is listing input this to center. I'm gonna just do is equal to this. Dist to center is equal to, let's see, we're gonna say listing dot pop. And then we're gonna do listing dot pop again. 0. And then we should have, I'm going to create a minimum nights bucket. Just going to look something like this, just for time. This is also, we did all of this already. I'm going to just copy this. This is the encoding that we have to do. And then lastly, we're gonna do LF prediction, which is not LF, sorry, LR prediction, linear regression prediction is equal to impimp, because we're again, it's training based off the log, so we want it to actually predict the actual value, and so we're just gonna transform that by doing predict, taking the exponent of the predict, or raising the value to, raising an exponent to whatever this value is, or creating the exponent of this value inside of here will be the exponent, right? Given our base 10, I think. Is equal to mm dot x1 model dot predict, right? And then we're gonna say input df 0. And then we're gonna say, again, just for time, I'm gonna copy this. Oops. For my notebook. Let's see, does this work? Cool. And so I think we can uncomment this. Predict price. I think we can call it instead of prediction. Oh, come on. Let's see what this gives us. Function. Oh, brother. Oh. That's what, this is different. Whoops. So we're gonna actually call the function, printing again, because also getting tired. Let's see how we perform. Okay, predict price, prediction is equal to predict. How many do we have here? Sample listing. Oh, I didn't call fit for my one hot encoder, did I? Okay, let me see. So if we go up to should be here. And we're gonna basically say it should be here. And we're gonna say input the data frame. This should look good. Amazing. Awesome. So we have finished this part. We are going to export this Python script. I'm gonna pretty much copy everything. We're gonna have a new file that has pipeline.py. Let's see. Okay. So let's get rid of all of this. Get rid of this. Get rid of this. I think we can get rid of all of this, right? So it should be, yep, we're gonna get rid of this, all of this, clean data, anything outside of the return statement. Export data is getting completely chopped, right? Because we don't want this inside of production code. This was just for our own learning purposes. Get rid of this. Okay. So we can go up here to the top, I'm guessing. We are getting rid of this. Right. Getting rid of this. Getting rid of this. Getting rid of this. And we are getting rid of this. I might just comment this out because maybe we might want it. And we're getting rid of this. Nice. So now we should be able to go into our app and basically get our dashboard ready. I'm gonna uncomment out the imports, and we're gonna implement all of the different to-dos that we have, which should be just for reference, just because I want to get this done quickly. Alrighty, so for to-do number 2, let's comment this out. So it should be something like get raw data, get clean data, should be df raw, right? And then we want to say get engineer data, which should be df clean, and then we're going to just say it's equal to get trained models, and it should be off of data frame engineered. Nice. So we got like 20 more to go. Okay, so next we're gonna be doing for our tabs, we're gonna just do st.write f length of the data frame, df raw, this, and then we're gonna say rows, and then we're gonna just say df raw dot shape, which is what we did in the very beginning columns, right? And then we're gonna say st dot data frame df raw dot head 20, right? And then for our next one, it should be st subheader. Oh, we already got that. Data frame, which is going to be df raw dot dtypes, s type string dot rename dtype. And then we're gonna do something similar. I'm just gonna copy this because it's easier. We're gonna say is null dot sum right. We're gonna say null to number 5. We got, oh, this is number 5 down here. Nice. Now for number 6. Again, so I'll comment this. Uppers should be df raw price. We did all of this already, so I hope this should be pretty self-explanatory. And also, I think we did like 99.01. Outliers is going to be df raw, right, price, and then we said anything greater than upper. Can I format this? Nice. I wonder if, does this work? Let me see. Let's see, does this work? Cool. So this is what we have so far. Let's put this up here. Oops. We'll just go left anytime. So to do number 6, we got that. To do number 7, let's see, comment these out. What did we do? I'm just gonna copy these because this is not anything Streamlit related. Number 8, I also hate having to deal with all this stuff. For 8, we're gonna just do, let's not comment this. We're gonna say outliers, neighborhood, room type, and then price. And then we're gonna say dot sort values, price ascending is equal to false, and we're gonna do dot head. We want to get the top 10 values from that, and then we're almost there, and we're gonna say df clean dot head is equal to 10. Amazing. I think we're still on, we're on the cleaning section. I wonder if you have to keep, let's just keep going and let's see if it updates. So with explore, nothing there. Explore, we gotta do all the plots and stuff. So we're gonna do fig, fig axes, plt dot subplots, fig size is equal to 6.4, and we're gonna say df clean price log dot hist bins is equal to 40, ax is equal to ax, color is equal to, we're gonna say hashtag 106 AB9, perfect, ax.set label, x label, log price, ax.set y level is equal to count, st.pyplot is equal to fig, and we're gonna copy this for next one for call 2. Let's see. This is number 11. We got df clean neighborhood dot value counts dot head 15 dot plot kind bar h. Oh, I love this. This has all the autofill, which makes it so much easier. Color is equal to, let's say, hashtag 10b981. Axis.invert, invert axes, invert y-axes, and then we're gonna say st.pyplot fig. Great. This is update. I think we have to cancel. We have to kill the terminal and then let's see. Oops. Okay. Yeah, there we go. Amazing. Alrighty, we have 2 more to-dos left and we're done. So for 12, I'm gonna do, let's copy this and we're gonna say 8 and 6. Okay. Scatter is equal to ax.scatter df clean longitude longitude df clean latitude what else c is equal to df clean price log, dang, s is equal to df clean. I think this is exactly what we did. Number of reviews divided by 10. I think we do plus 5. PLT dot color bar scatter ax is equal to ax label is equal to log price. And I think for 13, to do 13, we're gonna say core is equal to df clean dot core numeric only is equal to true. Oh, this is going so much faster now that the autocomplete is working here. np dot tree np ones like dot ones like core d type. I think a lot of this stuff you can also copy and paste from the notebook. Is equal to pl.subplots with s, fig size is equal to 9, 7, comma, and so we have s and s dot heat map core mask is equal to mask. CMap is equal to RDY, capital Y, LGN. Center is equal to 0. Square true. A lot of this stuff is literally, even though I guess it's different libraries, right? Because we're doing this. Well, this is the same library that we're using, but because we're using Streamlit, some of it is different. However, if it is different, it's basically one-to-one. I would say, okay, to do 14. Sorry, I took a break. Okay, let's get back to it. Fig AX is equal to PLTL subplots. Fig size. I'm gonna copy this. Okay, fig size. DF engineered. This to city. To center, sorry. Dot hist. Bins is equal to 40. AX is equal to AX. B981, something we already did already. AX.set X label. X label as distance to city center. Whoops. st.pyplot figure or fig. Next we have 15, which is almost the same. Engineer min night bin dot value counts. And instead we're gonna do plot kind bar x is equal to ax, colors equal to no b 91. Feel free to choose any color that you prefer. We gotta do pl.xticks is rotation. And then let's see, subheader. Oh no, that's all. And then this one's gonna be pretty easy. sc.data frame df engineered dot head 10. Great. Then okay, last 5. Alrighty, so after this we're gonna say, let's comment this, evaluate model, model.lr, xtrain, ytrain, xval, right? Xval, yval, xtest, y test. And then we're going to copy this basically. And instead, we're going to say rf. Next is going to be building a comparison data frame, which is comparison df is equal to pd dot data frame. Okay, so model, is this right? Yeah, model, random forest, comma, asterisk, eval, rf, let's see, and then, oops, we gotta do dataset index. Model. Perfect. 19. st.metric. Random forest. If you want to, you can get r squared from there, but then sorry, you can get r squared probably like pretty printed somewhere. Maybe if you just, I don't know, in Google or something, ask for the exponent to be pretty printed. I think you can probably get that and get that printed inside of here. But let's see, eval rf should be test underscore r2. This should be .3f. Looks good. And then we're gonna say, whoops, we're gonna say st.caption. F train r squared, right, is eval rf train r2 3.3f. The reason I'm really not explaining a lot of this stuff, and maybe I could have left this already filled in inside of what I had, but because a lot of the stuff we've already pretty much talked about, right? And so basically what we're just doing is putting into words what we've already talked about. Alrighty, I think we have how many? Just nice. So basically you should be able to copy this, right? And then just do it for linear regression, typical for linear regression. I'm gonna actually just copy this. This is it. There we go. And then for 21 should be, so the importance data frame is equal to pd.dataframe feature xtrain.columns importance, right, which tells us how important they are. Model.rf dot feature importances, comma, should be all good. On the data frame, we want to do dot sort values, importance, ascending is equal to false. Whoops. Dot head 15. Let's see, format document. Looks good. Alrighty. And then I want to copy something here. This should actually be, we're going to make this a bit bigger. 8 and 6. And we're going to just say, whoops, ax dot var h. Actually, I'm going to copy this again. And then we're going to say, very last one, right? Our last one should be, so, I mean, for me, I know that you all don't understand random forest well because I did not go into it, and we will go deeper into it later in the course, but I think what you could just say, right, as you're learning it, getting into this, is to say that the error for the random forest is the stronger model, because the error for the random forests model is lower. That's why you would rather go with random forest rather than linear regression. But if you want to go with linear regression because that's what you understand more, I think that's totally fine as well. And so just to tie this all up, we got result price is equal to model LR, model RF. Whoops, let's close this. We're going to say encoder, which should be in here, but I don't see it. Oh, did I get rid of it? And the get trained models. Let's see. Oh, that's weird that this is not in here. But get trained models. We're gonna edit this to also have the encoder. I don't know why that was missing. I think maybe I deleted it on accident. But here you go, encoder. Should be listing input, and then it should be xtrain.columns.toList. Let's see what's going on with this encoder really quickly. Oh, I forgot to return it. It should be in here. And then this should be, looks good. And then we're gonna say our metrics, which is, I'm gonna, again, just copy this so that you guys can see it. I'm gonna do call 1, call 2 is equal to st.columns2, and then I'm gonna print this out. Oops. Let's format document. What's going on with this encoder? This is crazy. Weird. Oh, looks like I forgot to. Where's get trained models? There we go. Encoder. Are we good now? All right, let's see what this is all looking like. Let's see. All right, something's broken. Oh, I'm sure we forgot to do df engineered. We forgot to probably add in. Oops. No, I wanted df engineered. And 57. 1, 2, 3, 4, 5, 6, 7. Oh, I think what we did not do is we did not return the encoder here. Is that what this is bothering about? Let's see. Let's see, can I? Nice, okay, amazing. Looks good. And this is our final, whoops, looks like we got something broken there. Let's see if any of our other pages have something broken. It looks like it's maybe the same thing. So 266, let's see. Oh, this should be linear regression rate. It should be random forest regressor. Let's see. Whoopsies. Non-type. All right. Gotta fix that. 274 now. Let's see. Oh, what we forgot, we didn't return anything in this. So this is what we're gonna, when we were editing this, we didn't actually have a return value. So let's do this. We're gonna say, oh, we did not do this right. They should be dollars. Right, and let's see. I'm not really sure also how to get this to automatically update. Let's see. Nice, no errors. And this all looks about right of what we saw when we were first exploring the data, right? So looks good. I think, is there like a dark mode? There you go. I think I prefer dark mode. But yeah, here's the final project. And I think to deploy it, what you can do is like, it'll give you instructions on how to do it. You have to push this to your GitHub repository, and I think I'm reluctant to press deploy because I don't want it to deploy because I already have something. So once you get deployed, it should be super simple to do. I think when I did it, it took me less than 5 minutes. But yeah, this is our app predictor, and let's actually go in and predict something. Let's say we're going to be in the loop. I'm not really sure what latitude is. Does it update when you do this? Let me see, Lincoln Park. I'm not really sure. Maybe we get rid of longitude and latitude. It's kind of hard because if you don't know, I'm not really sure. It's weird. You'd need to, I think what another thing you would need to do if you were to take this further would be to either get the actual longitude and latitude mapping for each of these neighborhoods and play around with this. But let's just say for now, the loop, which is going to be super close to it, this is going to be more or less around the same, and then we can play with the reviews last month. We can say it's 5, And then let's see what our predict price gives us. Whoops, something's broken. All right, let's see. I think so. In predict price, we have 1, 2, 3, 4, and then I don't think we actually need the encoder. Let's see. Also, if anyone knows how to get this to auto refresh, I'm honestly not sure. Let's see, does this work now? Let's say 12. Play around with it a little bit. 5. 22. Let's see. Oh. All right, let's see. I know what's happening. We have to do this. This should be the what's going on. Yeah, let's see. Let's see. Oh, is it auto rerun? Is that what I need to do? All right, 9. Let's see. 32, 33, 7. Nice. Okay. Amazing. So this is it. Thanks a lot for joining me today on going through chapter 2, and I'm looking forward to seeing you all in chapter 3. Thank you.